Okay, so I want to follow up our discussion about electromagnetic radiation and the transport of thermal energy, the transport of energy through heat, with a discussion about the greenhouse effect and how does that work with our planet and whatnot. So, first off, well, let's run through exactly how does this work. Our sun emits, it's that 5800 Kelvin temperature black body object. It emits a spectrum that we showed in the previous video, runs from radio through visible into ultraviolet and a bit beyond. It's a little dimmer in the higher energy parts of the spectrum. But then that energy encounters our atmosphere. And different colors of light have different effects as they encounter the atmosphere and the planet. Now, with radio waves, we know that the radio has to be something that passes through the atmosphere. We can talk to our spacecraft. We were able to talk to the astronauts through radio waves when they went off to the moon, and the spacecrafts that went out further and beyond. In this picture, the space station is actually kind of in the upper reaches of our atmosphere here, but it's a model and so on. This, by the way, over here, this is the surface of the Earth. So here's our atmosphere. Ta-da. Clearly, visible light has to get through the atmosphere, or we wouldn't be able to see the sun and the stars and the planets. So visible light does get through also. And visible light has to get through on the way up. It has to be some of the light that gets reflected off the planet also, because we can see the planet again when we look back at it. We see the surface from reflected light. And you can bounce radio off of it also. So radio waves, visible light get through. You can get sunburns and suntan. We know some ultraviolet gets through as well. The lower energy, the lower frequency of ultraviolet, the part that's closest to the violet part of the spectrum, gets through. But a lot of other colors of light don't. A lot of other colors, most of the infrared, bounces right off the atmosphere. And it's a really good thing that a lot of the ultraviolet and X-rays and gamma rays also bounce right off the atmosphere. Or we would get a lot more incidences of cancer and radiation sickness, and that's one of the things that makes it hard to design missions to send astronauts off to even the moon, but particularly further away like Mars, because you have to deal with all the stuff like radiation that the atmosphere would otherwise protect you from. But then we get light hitting the Earth, and the Earth is not a perfectly white ball across the full spectrum. It doesn't reflect everything that lands on it. It absorbs it. And you feel the temperature, and the temperature of the planet, maybe the temperature of the planet's around 300 Kelvin, or like 60 degrees Fahrenheit or something like that, for average surface temperature of the planet, somewhere in that area, let's say 50, 60, I don't know, ballpark. But what that means is that it's got reflected light, but some of that energy has hit the Earth and has been absorbed and is being re-emitted. And it gets re-emitted as infrared. So we get these longer wave infrared waves that that get trapped by the atmosphere. So some of the energy that left the sun doesn't, and that makes it through our atmosphere in the first place, doesn't make it out again because it's changed colors. The energy from it has changed colors as it interacts with the Earth. It's been absorbed by the Earth and then turned into thermal energy, and then the energy is re-emitted as heat, as infrared light, and infrared light couldn't get in and it can't get out either. So it's stuck there, and we hold on to that heat. Now we gradually radiate away some other energy through the upper atmosphere, and so it's not a straight ramp up, but clearly the amount that we're holding on to has been increasing. So we see with planets like Venus, Venus has an atmosphere that is 90 times the pressure, the surface pressure on the ground, as that of the Earth. So it's like an equivalent surface pressure to being about 900 meters below the surface of the ocean. It's really dense atmosphere. And you look at it with a telescope and you can see it's a really thick atmosphere in that sense also. The light, the visible light, doesn't get through from the surface. It bounces right off. That's why Venus is so bright, is all the visible light off the sun bounces right, a lot of it reflects right off of it. Some of it's clearly getting in. But once it's in there, even though its surface is a lot hotter than the Earth, it's stuck there. And so that's why Venus's surface temperature across the whole planet, no matter the season, is hotter than the day side of Mercury. And Mercury's days are almost as long as its years. So Mercury has like one side will face the sun for about 40 days or so. Even so, Mercury's got like no atmosphere. And so it'll heat up during that time and cool down on the night side a lot. Venus, it just heats up and it stays there, and it's hotter than Mercury, even though Mercury is almost twice as close to the sun and it's like 3 times as much energy coming in. But we need some greenhouse effect on the Earth, or things would be much less hospitable, even if we could breathe. We go to the moon, and the moon, the temperatures on the moon, where there's basically no atmosphere, can get to be like 200 degrees during the day, which will last 14 and a half days, to 200 below at night, which also lasts 14 and a half days. And it's going to be very extreme there. The fact that we have some greenhouse effect moderates our temperature going from day to night, keeps us from getting too hot and too cold. But the amount of the greenhouse effects changes, then we can get some climate change that can happen more rapidly than our species can adjust.